Thank you everyone for joining us for this webinar, Basic Soil Mechanics for Trail Building. My name is Candace Gallagher and I am the Director of Operations and Webinar Coordinator for American Trails. This is our 257th webinar in the American Trails Advancing Trails webinar series, and this is the first of 3 webinars in a series that we are hosting this fall and winter in partnership with the Professional Trail Builders Association. And this webinar is being recorded. It includes real-time closed captioning in English and also offers free learning credits. And you will see a link to the quiz and the survey in the chat box. And you can turn on captions by clicking on the CC button at the bottom of your Zoom window. And if another language is ever needed, please just let us know. And attendees will receive a follow-up email from me within 2 days that will include a link to the recording, the transcript, the resources slide that will include the presenter's email, as well as learning credit details. And I want to thank our webinar partners, additional webinar partners today that include Washington's Evergreen Coast, iZone Imaging, 5280 Creative, the Bureau of Land Management, the National Park Service, the USDA Forest Service, as well as the Grisberger Fund. And the Grisberger Fund is a donor-advised fund that belongs to 2 regular working people who really love trails, and they encourage everyone to learn more about donor-advised funds and how to use them to increase support for American trails and the free education that we provide. And so now I'm happy to introduce our presenter for today. We have Alex Mann, who is the owner of Trail Tutors. And before I pass it off to Alex, I want to hand it over to Erin Kay, who is the Executive Director of the Professional Trail Builders Association.
Thanks, Candace. We are excited to launch our 2024-25 webinar series with American Trails with this webinar on soils. A little bit about the Professional Trail Builders Association. We are the trade association for the trail industry, so we represent private sector companies who specialize in trail design, planning, and construction. And every company who has joined PTBA has been professionally vetted through a portfolio submission and peer review process. And all of the presenters in our webinar series are part of the PTBA. Next slide. I just wanted to share kind of the distribution of our member companies. So mostly in North America right now, but we have a growing contingent in Australia and 134 member companies worldwide. Next slide. I also wanted to share our impact from 2023. So our companies do work on trails, most of them full-time. And with that, you can get a lot of trail on the ground. In 2023, our member companies built more than 1,500 miles of trail, designed more than 2,700 miles of trail, led 180 trail trainings, produced 165 master plans, built 120 bike parks, and 21,000 feet of bridge. And as you can see from the list of where we work, it's all over the world. Next slide. And lastly, I just wanted to share, we ask our members every year for the last few decades on, their information. And it just shows, to us that the trail industry is really continuing to grow. And I just wanted to share these statistics that come from those member surveys. So just in the last 5 years, we've seen 424% growth in PTBA member company revenue. And I just wanted to highlight that because not only, does that show growth in the private sector of the trail industry, but it also represents that communities are investing in trails around the world. And that's pretty exciting. So now I'm pleased to introduce Alex Mann. So Alex holds a PhD in soil mechanics and a master's in environmental engineering. So this, educational background combined with passion and then decades of working in trails really brings a significant insight to the current trail building issues and their solutions. Alex Mann's company, Trail Tutors, is a member of the PTBA, and Alex has presented on this intersection of soils and trails at many of our conferences, even before joining the association. I want to thank Alex for offering this webinar and sharing his expertise, and I'm pleased to turn it over. to Alex right now.
Thanks, Aaron. Thanks, Candace. Hello, everybody. Just before I start, I just wanted to quickly acknowledge landscape architecture firm Scatliff Miller Murray, who convinced me 9 years ago to become a professional trail designer. Before that, I was a geological engineer for about 20 years, earned my PhD in soil mechanics, as Aaron mentioned, and I built a lot of trails as a volunteer. So Scatliff really basically let me combine my profession and passion and have a wonderful career. It's fantastic. So since then, my wife and I, we've spun off Trail Tutors, which is a trail design firm, and happy to be here presenting this. Of course, my keyboard will not work. There we go. Okay, so today I'm going to talk to you about soil with a few objectives that I hope will help in the trail world. First, we want to understand the soil triangle and how to identify all its components. If you've read any of the IMBA textbooks, it's all kind of introduced there. But we're going to go a little more depth and kind of cover the first few lectures of an engineering course in soil mechanics. So I'll try to keep it as simple as possible. It really is a lot of just common sense. And so we're going to look at grain size distribution curves. We're going to go over how engineers classify soil and understand soil phase relationships. So that's the soil particles, the solids, the liquids, the gas. Then we'll discuss compaction. Unfortunately, you can't feel my soil samples through a webinar. We like to do this at a course called Terrain Dynamics that we do at the PTBA course annually. So Mike Shields and myself will be doing that this April at the International Trail Summit. So if you like what you're seeing, you want to actually touch some soil, we can make that happen. I have my soil in front of me. I'm going to probably make a bit of a mess here, but I'm questioning how much you'll actually see when I do that. It's just more for my own comfort, I think. So let's jump into it. Soil triangle. There are three main components of a natural soil: sand, silt, and clay. And depending on the proportion of each component, you can get different names. So in this triangle, up at the top, right at the peak, you'd have 100% clay. And as you move down this axis, you get less and less. So 90, 80, 70, 60, and so on. So same thing for sand, 100% at the point, and then less as you move down. And same with silt, 100% at the point, and less as you move up that axis. And then wherever you land in the middle gives you a different kind of name. And we have a number of them, but they can be tricky when you're in the middle there to actually identify. So we're gonna kind of focus on the three main components of the triangle first to give you a feel for identifying them. So first thing you got to do is really get in there and feel the soil. So there's a number of field tests you can do. Feel method is it. It's the starting point. So you can think of these pictures as kind of grading from crunchy peanut butter to smooth. You can feel that grit when you have some sand. It becomes a lot more smooth when it's just silt, and it's almost buttery when it's clay. So yeah, we'll talk about these field tests kind of as we go, and something you can do at home, and then some of the lab tests later on in the presentation. So sand's pretty easy. You can see the grains. You with your naked eye. There's a gritty feel. It's really loose when dry. It forms a ball. I don't know if you're going to see this. Forms a ball that easily crumbles. So this is just a moist sand. And if I do what's called the fall test and throw it from one hand to another, it just falls apart. So if you have some clay in there or some silt even, it will more readily stay in a nice intact ball. So that's your first field test right there, ball test. Also, there's these geotechnical gauges out there that can kind of give you a little calibration to your eye of what size of sand you're looking at if you're getting down to that kind of detail. So what are the benefits? Sand is highly permeable, which means you're going to get good drainage. It has good load-bearing capacity. And it really increases the shear strength of a soil mixture, especially when you can get those particles kind of interlocking amongst another. Challenges, there's no cohesion. So cohesion is what's holding things together, and it means it does not, sand just doesn't hold its shape. So for that reason, it erodes readily by fast flowing water. And there's really a narrow range of moisture contents where it's fun to walk, run, or ride on. I mean, walking on the beach is great, but it's maybe not your best trail material. And it can be really loose in dry climates. Silt, it's basically just smaller sand. It's ground down usually by glaciers. It's small rock flour. Technically, you can't see these particles readily with naked eye. Some eyes are better than others, but that's generally the visual cutoff. So it's not really sticky. It crumbles easily. It feels smooth and powdery. And we have what's called the dilatancy test that we can use to help identify it. And to make you remember it, I'm going to call it the shiny poop test. So you roll yourself a little turd of silt in your hands, and all you do is knock one hand against the other. And if it's a silt, it starts to shine. So it's releasing that water that a clay simply won't do. So that the photo that's on the screen right there actually shows it quite nicely. It's shined up really good. So that's the shiny poop test. Benefits. The real benefit of silt is its soil retention capacity. It's much higher than sand, so it's going to help your soil maintain that moisture and help with that kind of glue that it offers. And we'll get into why it's that kind of glue later on. So it really helps with soil mixes. Challenges, very similar to sand. There's no cohesion. It's basically dust when dry, so there's very low dry strength, and it erodes quite easily. Clay is a totally different animal. The term clay refers to two different things, both the particle size, so it's now smaller than silt, but clay also refers to a mineral type. So a clay mineral is it's a sheet silicate, so it's layered silica sheets with aluminum sheets, and because of that structure, it has an electric charge on its surface. So you can imagine these as little tiny cornflakes out there, and with a little electrical charge on them that attracts water. So water can become part of its mineral structure, basically. So easily forms in a ball, stains your fingers. Dry clods are really hard. Like it's basically like a rock. It's like it feels like a rock. Does a good ribbon test, which I think everybody's done as a kid. You get a pile of wet clay and you squeeze it in your hand and it shoots out the top of your hand like a ribbon. My IT guy hates it when I do that near my computer. So I'm going to defer to what I do the most and make worms. So if you take a soil sample, and if you can roll it into a 3 millimeter, or in American, about 1/8 diameter roll, then you definitely have a high clay content soil. So that's almost what I do first whenever I see something that I'm questioning as a clay or not. So benefits, here's where we get our cohesion. Clay offers that. It has that high dry strength, so that rock there holds its shape. So for trail features, you can build your berms, rollers, and jumps, and it does pretty good in dry climates too. Challenges, it's the problem with clay is it was deposited in a flat, low energy environment like a glacial lake or a seabed, and it wants to get that way. So if you wet it up again, it just wants to be flat. So clay slopes tend to fail pretty quickly. Just low strength when wet. It's slow to drain, so it's taken long to dry. And I don't know if you've ever dealt with ruts in a clay trail, but they're really, or footprints, they're really difficult to fix. And obviously it gums up bodies and bikes and equipment. This picture, I just wanted to show it really helps when you're trying to distinguish between silt versus clay. So at the bottom where that 3 is written, that's smearing through a clay. And just above it is a pocket of silt that just crumbled right out. So that crumble versus smear is a kind of a key helping point to distinguish whether you've got a silt dominant or a clay dominant soil. But we'll talk about that a little bit more when we get to engineering classification. This is just a summary table for reference. You can all have my notes. But basically, we have sand, silt, and clay, and they all have their strengths individually, but they're not great by themselves. So the question is, what's the best mix for trails? And there's a general consensus. There is a sweet spot, and it's a soil called loam. And we're looking at the ranges of 50 to 30% sand, 50 to 30% silt, and 25 to 10% clay. That small amount of clay makes a big difference. So now we're getting that cohesion from the clay, so it's holding its shape. We were getting capillary forces from the silt, so it's got that water suction. It wants to hold onto the water, and we're getting that drainage and shear strength from a sand. I got a chunk right here. I know you're not gonna appreciate it, but it's really workable. It shapes and compacts really nicely. If you have too much clay, and I just dealt with this on a project, it's hard to shape and it's hard to get a nice smooth trail tread. It's just not as workable. So unfortunately, we can't go out to an area and say we want perfect loam on our trail project. It's rare to get the perfect soil at any trail or geotechnical project. Structural engineers out in the world, they're blessed in that they get to go and specify the type of steel, the shape, the geometry of all their beams and everything. In the geotechnical world, we don't have that luxury, nor do we in the soils or the trails world. So we have to go out and investigate the profile, test our samples, do some analysis, and then design accordingly and build. So further, we don't always get those easier to identify sand, silts, and clays. We're faced with a much larger grain size out there, from boulders that are basketball sizes and larger to coarse sand or coarse gravel and baby head sized cobbles. So what I want to do is talk to you about 2 key tests to quantify that, and both of them produce what's called a grain size distribution curve. So let's talk about those. So for coarse grain soils, this is basically a stack of sieves where the top one has wider openings, and you grab a sample, you dry it, and you throw it in the top, and you shake it. So it shakes for a good little while. And as that happens, the sample starts to fall through the openings in those sieves, and they get caught on certain sieves based on their size. So you can take those sieves apart after you're done shaking them, and you weigh the amount caught on each sieve. And that basically gives you a percentage that was caught on that sieve. So from there, you can graph it. The very bottom one, the 200 sieve, that differentiates fine grained soils from coarse grained soils. So silts and clays, they're both finer than 200. We have a different test for that, and we'll get to that in a minute. So this is a well-graded sand with lots of variation in particle sizes. So starting up at the top, 9% of them were caught on that top sieve as pea-size chunks. Then 11% was caught on the next sieve, and that's about like sea salt size. Then 32% sugar, 32% fine sand, and you can just see this stuff with your eyes. So it's basically just above that silt mark where you're not quite powdered, but you can see the individual grains. So at the very bottom of this sample, 16% passed as fines. You can't see these, and this is what we need another test for. Note that the most of the drop happened along the top there, fine to medium sand. So where you see your curve drop the most, that's what it's going to be called. So in this case, fine to medium sand. So the beer and winemakers out there will know what this is. It's called a hydrometer. And this is what we use to measure the grain size distribution of anything smaller than that 200 sieve. So basically, it's like a milkshake of mud. You shake it up vigorously into a slurry. You drop your hydrometer in it, and it floats. And it's graduated to tell you how much has fallen out of that slurry at a given time, basically from calibration. So you can go and come up with your same grain size distribution curve. But you can do something like this at home really easily. And it's called a jar test. And I find it really, really helpful. So you take a sample of your soil that you're dealing with for your trail project, throw it in a jar with a bit of detergent, dishwasher detergent, and shake it up, and then just let it settle overnight. I know it's going to be really hard to see in this, but in the next morning, you can see the sand settle at the bottom. You'll distinctly see the grain sizes. Then you'll generally have two different colors between the silt and the clay. They're both kind of milky layers that flow a bit like a lava lamp, if you see closely, but it lets you kind of get a visual percentage of each one of those. So it's a handy little test to do back at home. So here's just some examples. This is a silt. So it's 62%-ish silt and a good chunk of clay still. But here's where that largest drop happened through that silt range. And here's a clay sample where it's pretty much 99.7% clay, just a touch of silt. So basically everything's finer than all the sieve points above that. So it's a lot of clay. Before we go on to engineering classification, we need to chat a bit about grading. A well-graded soil means there's a wide range of particle sizes present, okay? Poorly graded means a high proportion of particles they're all the same size. So in this diagram, you can imagine like that poorly graded sample, it's like walking or riding a bike on a pile of ball bearings, whereas the well-graded material has little wedges in between those larger chunks that actually lock that soil together. So you'll hear that called like binding. To confuse things, engineers and geologists use totally different terminology. And you just have to kind of pick one and get used to it. Well-sorted beach sands are let me reverse that. Poorly graded soils like that all ball bearing thing are well sorted. So in geology terms, they look at geological processes, sorting materials. So like a beach, it's just going to wash back and forth, and you're going to be left with a similar size material, and smaller grains get taken away. Poorly sorted things like glacial tills just haven't had that kind of energy imparted to them, so they end up having representation from a larger grain size distribution. So they're not sorted, they're poorly sorted. Okay, now we have everything we need to move on to engineering classification. Here are the main systems used in the world. The top is the British standards. Next one's the Unified Soil Classification System. Then the American Highway People, and ASTM, which I'm sure a lot of you have come across. But note that the soil triangle here is basically half of this classification system. So we have sand in the middle there, silt, clay moving to the left, gravel, cobbles, and boulders off to the right. So we're now incorporating the soil triangle plus all the other things that we might find in the soil. We'll focus on the Unified Soil Classification System. It's pretty commonly used, and it's kind of like a two-letter system where the first letter corresponds to the primary soil type. So G for gravel, S for sand, M for silt. I have no idea they picked M, but they did. C for clay, And then you can have organic soils and peat as well, which are things that we don't really deal with much in the trail world. We want to get rid of that. The second letter describes the grading of the core soils. So that's why we needed to have those couple slides there. So well graded, poorly graded, you'll get those two letters combined together. And the second letter for fine grained soils, so for silt and clays, we're going to be talking about plasticity. So we'll get to that. So this is just a chart, a reference chart that you can look up, and it's just for an example. So these two-letter group symbols, you'll get things like GW, GP, but you'll find those on borehole logs and maps frequently. So just good to see it, but you can use this as reference. So back to plasticity, what does that mean? Plastic behavior means that it will hold its shape after being deformed. In contrast, elastic behavior means that it'll rebound to its original shape. Okay, so we're looking at basically deforming a sample of soil, and does it hold its shape after? So clays and silts can have some plasticity. So this diagram basically shows the states that a clay or a fine-grained soil can go through as you increase water content. So at the bottom of that diagram, you can have that state where it's rock solid, and then you can move up and slowly add water where it becomes semi-solid, and then it becomes plastic, and then at some arbitrary number, which we'll kind of define in a minute, it can become a liquid. So the limits between that plastic state at the bottom there, it's plastic limits. So it's now behaving as a plastic. And then the top of that plastic state is the liquid limit. Okay, we're going to talk about how to define those. Almost an embarrassing test. It's like running a jack in the box. So what this is a cup that we try to find the liquid limit of the soil in. And basically we add water to the soil, mix it up, put it in this cup, and we groove it with this little grooving tool in that person's right hand. And you turn the jack in the box and it drops that cup however many times as it takes to close that groove. And the magic number for the liquid limit arbitrarily is 25 drops. So we do a number of trials until we get that line established and define where did that groove close and what moisture content it closed at. So once we get that 25, we throw that sample into the oven, weigh it before and after, and you get your liquid limit or your moisture content that happened at liquid limit. Okay, so that's just defining liquid limit. Plastic limit, we go back to the worms. So roll a worm until you no longer can, and it starts to crumble. And that's the lower limit of that state. So it's not acting as a plastic, it's acting as more of a semi-solid when it starts to crumble. Real technical stuff compared to the structural engineers, right? Okay, so one more thing to define. So the difference between that plastic limit and that liquid limit. So if I go over here with the cursor, plastic limit's down here, liquid limit's up here. Clays will behave like a plastic over a large range of water contents. So remember I said it incorporates water into its mineral structure. It's doing that and allowing it to, it's actually preventing it from becoming a liquid very quickly. In contrast to silt, you start adding water and this plastic zone is going to be a lot smaller. So the difference between that plastic limit and liquid limit is called the plasticity index. So that IP, okay? These are just some examples and kind of referring back to that same photo I showed you earlier of the silt and the overlying the clay. This silt sample, 60-ish% silt, had a liquid limit of 26-ish% moisture, and the plastic limit was 20%. So that gives a plasticity index of 6.6, pretty low. And then we go and take that to what's called a plasticity chart and just plot it on this. Again, this is for reference, but what you can see here is the 26.6 plotted down here and the 6.6 plotted here, and it gives us an ML. So that's a silt. M is for silt, L is for low plasticity. Okay. If we look at a clay, this sample is in around the 77% clay range. It had a liquid limit of 76-ish and a plastic limit of 31. So now the plasticity index is up at 45. So quite a bit higher than that last sample. So we'll go and plot that again on the same chart. And now we're getting the 76 over here, puts us against this 45.2 up here. And now you're plotting in the zone of CH. So C is for clay, H is for high plasticity. So all that classification system stuff still can be described even further. So when you're out there, don't forget the other things. This is just my cheat sheet that you can all use. Describe all the other things you're seeing, like the consistency, compactness. Is it really dense in the field? What's the moisture in the field? What's the color? Are you seeing any structure to it, like layering or fissures or things like that? They're all worth noting down. Okay, so let's talk about phase relationships, which will help us understand what's happening when you compact your trail. Okay, soil is made up of solids, liquids, and gases. The space between the particles are called voids or pores, and they can contain the water or the gas. When the voids are filled totally with water, it's called a saturated soil. Voids are filled partially with water and gas, it's unsaturated. And when it's completely dry, it's just a dry soil. So just some obvious definitions that need to be stated. Now we can take the sketch to define density as mass per unit volume. And for most engineering or trail projects, we want to maximize that density. So how do we do that? We basically have to get all that air out and have the right amount of water. So we want to get those particles as tight as possible together. And yeah, the easiest way is getting that air out. Also, depending on how much water is in there, sometimes you have too much, sometimes there's not enough, and we'll get to that. Okay, so how does water help us? This might look a bit scary, but it is actually helpful. Along the bottom is suction, and along the, sorry, my cursor's on my screen, not yours. Suction along the bottom, water content along here. So up here, we have a saturated soil. So you can see the voids are all filled with water, and the particles aren't all touching. So you're probably not at your maximum density here. As you go down and lose a little bit of water, so you're going down this nice S curve. Now we're in this pocket here where there's some air in the voids, and there's probably some room to densify that soil. But more importantly, as you do this, you're increasing soil suction. So think of a meniscus in a straw, or if you overfill your glass and it's just bulging over. That's from surface tension that actually helps us in soil mechanics, where that tiny straw between two particles is actually pulling them together. The water is in suction, okay? After a while, if you lose too much water, it becomes dry and it stops giving you that benefit, okay? So compaction. Compaction is the densification of a soil through expulsion of air. And we want to do it because it increases the soil strength, it reduces settlement, reduces flow of water in the soil, and helps with better sheeting across your trail, reduces frost damage and erosion. So water plays an important role in this. Back to this. Let me get my cursor over there. So again, here we have no room for density change. Water is pretty much incompressible, so you'll be beating on that with a compactor, and you'll start to see puddles on your trail tread. So when you see that, you're actually not doing anything to make it denser. Somewhere in here, when you're in the sweet spot, you're going to have some room for density change. You're going to be able to compact, get that air out, and have some point where your moisture is actually pulling the soil particles together. So that suction is working for you. And then, yeah, further down the line, when you lose all your water, you're going to be compacting your soil and causing basically a dust storm. And when you're doing that, you're also wasting your time. So there will be a water content where you can get the best compaction, and we can measure that. And it's basically from doing a bunch of mini compaction trials. And it's called a Proctor test. So it's a mold, a soil mold of known volume, and you impart a known amount of compaction effort. So in this case, we have that's a hammer. It's a drop hammer that compacts your sample. And you do that for several different moisture contents. So you add some water to your soil, compact it, try it again, or measure your density, try it again with a little more water, measure your density. And if you do that enough times, you will see kind of a peak. So here's the compaction curve. So at the dry side, here's where your water content's increasing this way, your density is increasing upwards. At this side here, you're creating those dust storms, and then you're adding water, it's going to get denser and denser. And then you're going to get to a point where, okay, there's just too much water. Now we're smacking it and it's making puddles. Okay. And here's just some examples of various clays or soils. You'll note that gravels, they can be quite dense. So in the 2 to 3-ish gram per cubic centimeter range. Sands, you're still getting a nice defined peak. As you get lower though, like towards the finer grained soils, that peak's a little less pronounced and it becomes a little flatter. So, for clays, 100% clays, you can be hitting it like crazy and not really gaining a lot of density increase. This is just a chart for your reference. And it basically says that coarser grained soils like to be rolled or vibrated. Finer grained soils, they respond better to rolling or kneading. So those sheep's foot rollers tend to do a pretty good job, but not so much. The clays just don't do well with vibration or plate compactors. So what? Hopefully, as people in the trail world now, you can kind of take this information and understand some background before you get to a site, and look up some geology maps, geotechnical reports, borehole logs, university reports. They're all out there. You can show up with a bit of knowledge and read these reports and understand where the terminology is coming from. Yeah, now you can go out and sample and describe the soil at your site. Specify soil tests if you're unsure, and from that information, anticipate some problems and maybe specify changes to your mixes if you need something that just fits the bill a little better. And also hunting for bore material to help fill those gaps that you might have in the soil. So that is my full speed version of that presentation. Again, I like to do that with people in the room with me, and I can show them the soil. It works a little better. But if there's any questions, I'd be happy to chat.
Yeah, there's a few questions in the chat that I'll pass on to you, Alex. There's one question about rocks in the soil, or rocks, gravel, pebbles in your soil, and I guess how does that affect the soil? And then also many agencies fix problems by introducing gravel, and just kind of how does that relate, and is that a good strategy?
It depends. It can be. So rocks, so say pea size and a little bit bigger, like 3/4 down gravel. I was just at a project where I actually wasn't involved with it until they had a problem, And they called me in and said, why is this gravel so rough and bumpy and not barefoot friendly compared to another section, which was glass smooth, perfect, and it was the same material. And it 100% comes down to compaction at the right moisture content when it was installed. So the contractor that did that little top up on their new section really didn't compact it, and it was dry as dust. So I went out there, and all the coarser stuff ends up at the top. So you get one rainfall, and your finer materials are being segregated within your trail tread right there, right then and there. And you don't have much hope of bringing them back up. So you're left with kind of loose, larger chunks of gravel sitting on the top of your trail tread that are just, they're sharp on bare feet, and they're not fun to ride a bike on. And they're actually slippery to ride a bike on sometimes, and they hurt when you fall down. So the best bet, again, is just do it right the first time with the right amount of water, and compact and get that nice, hopefully glassy gravel trail surface. If you don't, and what I asked them to do was try adding some more finer gravel, so that it was a 3/4 down, that all the larger stuff was right on the top. So I said, well, try putting a 1/4 down gravel on top, just a small skim of it, to try to replenish those fines, but importantly, have it wet before, and add that new layer at the right moisture content. Hopefully that helps.
There were a couple of questions about the detergent jar test.
Okay.
One was, when the silt and clay separate in the morning when you're looking at it, which one is on top? Like, how can you tell the difference?
Oh, sorry, I totally glossed over that. Yeah, it settles based on grain size. So you're going to get your sand settling first, then your silt, and then your clay on top. And the clay can take a long time. If it's a lot of clay in there, it'll just look like dirty water on top. And sometimes it takes more than a day to get that distinguishing thing. But silt, it'll look like a kind of a flowing little layer, and it's often a kind of a milkier color.
And then there was another specific question about that, in terms of what kind of detergent do you use? Dishwashing, laundry, liquid, powder?
I think it doesn't matter. I think you just don't want a lot of bubbles. So I think the INBA books say just a drop of dishwasher detergent is enough. It's more to break up the clods of clay, because it has that electrical charge. So it helps with that. You don't want those larger clay chunks falling out with the sand, and then you get an unrepresentative visual or test. So it needs to be kind of ground up, and it's best if you grind up the sample a bit too, and make it kind of no big chunks of clay going in there. That helps.
And then, oh, great, sorry. So also kind of related to the jar test, just kind of big picture, what are we trying to learn, or what can be inferred from the jar test, you know?
Yeah, often it's just helping you get somewhere in the middle of that soil triangle. So a lot of people will just go and look at soil and go, oh, that's a clay, and it's not. It's some mixture of sand, silt, and clay. And we're trying to aim for that loam, that magic sweet spot for trail tread. So the jar test just lets you visually look at that and say, okay, how thick are those layers in the bottom of the jar? Do I have the right percentages? Is it, roughly 40, 40, 20? If you got that, then you're doing pretty good. But if it's, a little bit more sand, a little bit more silt, and just, a 10% clay, you might still be okay. So it just helps you visualize where you are in that soil triangle and how close you are to the sweet spot for a good tread. That's the reason for that test. And it's so easy. It doesn't cost anything except for your jar. And you don't have to pay for a more expensive lab test.
There's quite a few questions about working in sandy soil.
Okay.
And, I guess one is, how does that affect your design of a trail, in terms of sandy soils, you're working with that. Also, how can the sand be improved? Is there additives, whether local or someone references quicklime, to improve stability?
Yeah, I think it depends on your budget, right? Sand soils, they will be a problem. You really have to focus on sustainable trail building practices, which are not the topic of today, but really focusing on draining things gently, because otherwise it's going to take your tread away. So that's in absence of being able to make any changes to your mix. If you had the choice, you want to add some silts and clays. It's pretty difficult to do on a long wilderness trail, but maybe for a bike park or something like that, you can actually mix batches right on site where you are bringing in different soil types to get that magic mix that'll work a little better. Yeah, it's a tricky one, definitely, and I think I've even seen some trails where they're building them to hold water when they're largely sand based. So yeah, water helps. If you can add some silt, some fines to lock it together, even better. But not all budgets allow that.
So kind of on the opposite side of that, there's a question about if you have silty spill in a drought, so basically it's just the powder, and you're unable to compact, what can you do?
Unable to compact. Well, I have some predominantly silt trails, and I find the biggest problem with them is the spring when the frost comes out and they're super wet and it's like mush. So it's like stepping in mush or riding in mush. And then if there's any amount of clay in there, they just end up being rock hard afterwards, and your ruts are really bad. But compacting silts, you saw those grains or those compaction curves. Is as long as you're not creating that dust, and you have some amount of moisture, you're probably doing better than not. Even by hand, you'll help. Like, it's such a flat compaction curve that without some real good effort, and sometimes too expensive effort to bring a machine in, or maybe you can't, like you're saying, bring a machine in and you can't get that compaction. So do your best by hand and have just a bit of water in that. Hopefully that helps.
So there's a question about, what are the indicators that the soil moisture in the trail surface is at the appropriate or ideal level for compaction? And I think, in the field that someone could test or figure that out.
Yeah. Well, the puddles versus dust storm is your large bracket. Between that, it's either trial and error, and you can do like those mini Proctor tests on your own. Just grab some of the material that you're working with and make a pile off to the side and beat it with a cloud for a few minutes and add some more water and just see if you can get the right mix and kind of calibrate yourself for the field to do that. More budget-friendly projects might actually pay for those Proctor tests. And they came from the road industry, where it's really important. You want to have that maximum density under a road, and they'll do those tests, they'll pay for them, and then they'll actually measure the density of those road beds afterwards. We don't generally have that luxury. So going by feel is probably just as good, and just doing it is more than a lot actually do. So if you just play with it for an afternoon, a couple hours or whatever, you can learn a lot.
There's a question about, it says, my team has been working in terrain adversely affected by a forest fire and dealing with thick layers of ash on top of the soil, meaning that it routinely settles on the tread. And I guess the question is, what are some strategies to deal with that? And could there be any positives to the ash, or is there something we can do with the ash?
That is a really good question. And I have seen some papers probably within the last, I don't know, maybe 5-ish, 10 years that talk about soil degradation after a forest fire. And we've had a lot in like southern BC and Canada. And it really messes things up. Well, first of all, you're obviously losing your vegetation and it's not locking your soil down, but there is something behind that. And I don't have a good answer for you, but there's something behind that that may actually change the soil chemistry that will affect a trail for. I'm imagining the negative, but I like I say, I don't have a good answer for this, and I've been meaning to read into those a little bit more. So I'll try to do that for next time.
And so here's a question about if soil moistures are not ideal, do you recommend postponing trail construction or building trail but postponing opening to trail users? So I guess getting back at that compaction question, ideal compaction.
Yeah. Well, so the risk of opening it up before you got your good compaction is similar to what I was talking about earlier with the gravel. If it just wasn't compacted moist enough, you let people out there, and then a rain happens, and suddenly you're left with all the large particles up top, and you're not happy. In contrast, if it's just too wet and you open it up, it's probably going to be mushy. So I encourage builders or planners to get, before it's open, get that right compaction down. And sometimes it's down to the builder of timing it. They might have their roughed in trail built. They might have their tread delivered and spread on site, but they're waiting for the compaction for the right amount of rain. I've done that lots where it's coming, so let's continue moving forward on the trail build. We have this ready, and when the moisture's right, we're just going to hit the whole thing with the plate compactor, roller, you name it, and try to time it that way. If you have the luxury of doing it, you deliver the water out and sprinkle it on and build as you go, compact as you go. That's nice. And it also helps if you're traveling back and forth on your corridor. You'll have the densest possible tread to be traveling on. So yeah, I encourage getting the right compaction or right moisture for compaction before you go ahead and open it up.
There's one question about if you've seen any creative ways to get moisture to a site that's remote, where obviously it's not local.
Rain's always the best. The most common way I've seen it done is by ATVs with water tanks in the back and a little kind of like a trickle sprinkler thing on the back. I've also seen those firefighting backpacks used, which was kind of cool, but man, it's a lot of work and not a lot of water. Really, it's working with the Mother Nature and what rain's coming. That's what's most common, I'd say.
There's a question about organic material, and does adding organic material to the trail shed help, or is that simply a myth? Like leaving trim brush or leaving the leaves, or versus leaf blowing, kind of how does that play into tread and
so the canned answer for that from all the IMBA books and everything is get rid of the organics. And it's usually right. It's very compressible. It'll rot and leave opportunities for more water to get into your tread. It simply does not let you get your maximum density. So it's good to have it off. However, I've seen spots where it's created this wonderful mat across like a silt that's chronically wet, and where the organics were removed, it's just a horrible trail. Where the organics were left, it's kind of a nice matte nature trail. But it really comes down to traffic then. Is it going to be a high traffic trail? And if it is, then the canned answer is get rid of the organics and put something that's going to be really firm in there. But it is a tough question because I have seen it work, and I try not to admit that much, but yeah, the usual way is to get rid of it.
There's another question about trails going through a melt freeze cycle that makes them really fragile. So ice crystals pushing up on cold nights and then melt by mid-morning. And the question is, what's going on, and can it be mitigated by adding gravel?
What's going on is it's ice lensing. Silts are especially susceptible to that. So as the soil freezes, the water basically combines itself into little crystals that push the grain particles apart. So it fluffs your soil up. In the center of Canada where I am, we have a lot of fine grain glacials, silts and clays, and it happens a lot. When I build a new trail, I tell the client that it's going to fluff up every spring, but it's going to get better and better over time. So it does tend to slow down with really, really good compaction. And once a soil or a tread gets kneaded over time, it really helps. If you have the patience for that. If you don't, yes, adding a little bit of gravel will help with that. And if you want to keep it a nice fine grained thing, keep it maximum quarter inch particle size.
There's a question about the applications of undercutting and or geotextile separators and stabilizers as related to the soils on a trail. And I guess maybe your success, or have you used these strategies?
Yeah, I've used geogrid type soils for drainage layers, and actually that same project that I mentioned earlier with the silts that were exposed after the organics were peeled off, they ended up putting on a geogrid and filling that with kind of an aggregate, and it's been performing much better. So yeah, that geogrid does help.
And then I think we'll have time for one more question. And so it's a question about being in a coastal area with a high water table. And so many of the trails stay wet and muddy, especially during the winter months. And what is a suggested material or strategy to help add firmness to the trails?
Ooh, well, unfortunately, most soils, when they're completely saturated, they just are not as fun or pleasant. User experience is way down. Soils are just plain old moisture dependent, especially when there's finer grains, like I said. The strength and their behavior is moisture dependent. So that honestly comes down to sustainable trail building practices, where you want to keep that water off of your tread through proper grading, grade reversals, outsloping, crowning, that kind of thing. So that's the best answer I can give there, I think.
And there's a lot of questions about aggregate surface trails and as an additive. And I just wanted to call out that our next webinar in the series is on the fundamentals of aggregate surface trails. So we'll get into the details of that at the next PTBA webinar, which is in early December. Thank you so much, Alex. And I'll hand it over to Candace.
Awesome. Thank you, Alex, and thank you so much for moderating the Q&A, Erin. There are many more questions that we were not able to get to, so I definitely encourage you to reach out to Alex or Erin, or you can just reach out to American Trails and we can forward your question on if you still want to get your question answered. So I also, again, want to thank our webinar partners that include Washington's Evergreen Coast, iZone Imaging, the Grisberger Fund, 5280 Creative, as well as the Bureau of Land Management, the National Park Service, and the USDA Forest Service. And along with joining the next PTBA webinar that will happen in early December, we also encourage you to sign up and register for our next webinar taking place next week in the Advancing Trails webinar series, and a reminder to subscribe and support American Trails on our YouTube channel at youtube.com/American Trails. So thank you again to everyone for attending. I hope you all enjoy the rest of your day, and happy trails.